Oh, you know what, probably that other form was better, R naught minus R over H naught plus little r squared you can still go ahead and divide it, I'm not dividing there, plus little r times big R, which is H R sub naught minus little r over H sub naught plus R plus R squared. Any Carol's errors yet? All right. So I have H over 3, H pi over 3 times squaring that puppy. Gives me little h squared R naught minus R squared over H naught squared plus two H R naught minus R over H naught times R plus R squared plus the next term H R naught minus R over big H, so 0 plus R squared plus R squared. So far, so good. Let's combine like stuff. I've got R squared, and R squared. I've got, those are basically the same, and then I've got this sitting out by itself, so I have H pi over 3 times H squared, R naught minus little r squared over H naught squared plus 3 H R sub naught minus little r over H sub naught plus 3 R not cubed squared. Depending upon which derivative rule you want to do, I'm going to go ahead and multiply H, distribute the H throughout. I'm going to leave pi over 3 out of it. So pi over 3, so again, this is my volume 1. Pi over 3 times H cubed R naught minus R over H sub naught squared plus 3H squared R times R naught minus R over H sub 0 plus 3H R squared. So unless there's a careless error, give a dramatic pause for anyone here to pick out a problem. Dimensionally, it's okay. Bad notation there. All right, so a derivative. Here's dv1. Little h is a variable. If I said dV/dH, would that help you?
Is that 3h squared
Times that. You're on a roll.
times 2 plus 6h
Times that.
yeah, and then plus 3r squared.
All right. So if I multiply both sides by dH, I end up with dV1 is equal to pi over 3 times 3h squared r naught minus little r over h sub naught squared plus 6h times r little r times r sub naught minus r. I'm running out of room here. I'm gonna cut some space out and dH. If I divide by dt, because these are taking place over a certain amount of time, so I divide by dt, this is the rate at which I'm losing volume. This is the rate at which the height is dropping. That whole first part in the lab where you were filming the height versus time, that was so you can get this. So when you had height versus time, you end up with, I guess the height is dropping. So dH dt is just a slope. It is negative. So dV dt is a negative number, which makes sense because we are losing volume as time increases. Oh, actually, that's dV dt. So that whole mess right there, pi over 3 times what I have in the square brackets times dH dt is equal to A2V2. This is the speed at which it's coming out, and that is the area of the hole, which you calculated, cross-sectional area of the hole. Now, you did it differently? Did you get to the same place, or?
I ended up with dV dt equals, I guess, the velocity times the area of the hole.
Okay. Which is true. I assume your dV dt was d volume dt?
Yes.
Okay. Did you figure out how to figure out the change in the volume?
I don't know what I did after that.
Okay.
I guess I treated the slope as the velocity or something. I have no idea what I did.
Okay. Now, when I first showed you in lab, I noticed, I said there was something wrong with part of it, and there was. Just as a quick and dirty, because you took it every 5 seconds, so around 0 seconds, 5, this was time, 10, 15, 20. And then you would have dV1 dt. So this would basically be the change in the volume at each of these moments in time. If you do a crude estimate here, assume that each of these changes in the volume happen for 5 seconds. So instead of it being a continuous function, it's sort of a step function. So if you add all of these up and multiply times 5, you should get approximately the volume of the cup. The initial volume of the cup, the initial volume of water that you have in the cup. So that's how I knew something was off. Eventually figured out there was a careless math error. But once you plot height versus time, you can get an equation, and then once you get the equation, you can just take the derivative to figure out what the slope is at that moment in time. If you decide, I use a quadratic. If you use linear, it's really not that far off. It's pretty darn close to linear. But I felt quadratic looked better. Questions? Comments? Make sure it was recorded. So future generations can look back and marvel at, wow, that was the first group that did that lab. Man, they had it so easy, because now we have to measure all sorts of extra things. Because I did make the assumption that the outside volume was close enough to the inside volume, which I won't do in the next round. But it does run into the issues that you ran into of trying to figure out measuring anything at the bottom of the cup inside. All right, ready for Bernoulli? Bonus points in here if you can tell me which Bernoulli came up with Bernoulli's equation. There's like 8 famous ones.
The smart one.
What was that?
The smart one.
They all had, indeed, were the smart one. All right, you get a partial bonus for getting here. I was going to say Daniel Bernoulli, but then the question is, which Daniel was it? And I don't think I have those papers here. So imagine if you will, I've got a pipe here with a fluid going through it, and the pipe takes a bend. Into a smaller cross-sectional area. Similar to what we did before, except we're taking a change in height here. I have some area, call it A1, and a piston that's pushing on whatever the fluid is. So I got some fluid in here. I got a piston over here. Piston here. So this piston is going to push on the fluid here, and then the fluid's going to push on that piston there. I know that the total work that is done has to be the change in energy. Actually, try that one again. The non-conservative work is equal to the change in energy, which is change in kinetic plus the change in potential. Now, the work being done, we have this piston pushing that way on the fluid over some displacement here. So the work one is going to be the force by 1 times the displacement of 1, delta x1. So it's going to push the fluid. Over here, that fluid is going to be pushing this backwards. So the force, the work done by the fluid is some positive amount, but the work done on the fluid is a negative amount. So work 2 on the fluid is negative F2 dot delta x2. If it's not meant to be squared. If it is an incompressible fluid, continuity equation takes place, even though it's not drawn properly. The volume here is equal to the volume here in shade. We are dealing with fluids. So the force that's being applied here, well, it should equal the force that's being applied back, which is in magnitude, is equal to the pressure at 1 times the area of 1 times delta x 1. Sort of got rid of the dot product because I know that the piston is pushing on the direction that the fluid is going to move, so they're in the same direction. Up here, work 2 is going to be equal to negative P2A2 delta x2. I guess properly that minus sign actually should show up here. Because the force on the fluid is that way, the displacement is that way, so as a dot product, we get the negative. So, the sum of the total non-conservative work there, so I got P1A1 delta x1 is equal to, oops, try that again, minus P2A2 delta x2 equals, well, K final minus K initial plus U final minus U initial. Now this A1 x1, that's just the volume of the fluid over there. So I got P1 V1 minus P2 V2 is equal to, well, you should know it by heart by now. What's the formula for kinetic energy?
1/2 mv squared.
Mv final squared minus 1/2 mv initial squared. Formula for, well, which potential energy are we working with here?
Gravitational.
Okay, and what's the formula for gravitational potential energy?
GH.
So I'm assuming that little g is relatively constant. So plus mgh final minus mgh initial. Now when you're dealing with fluids, typically when you're talking about mass, it's less, we put it in terms of density, mass. So we have P1, well, let's do 2 birds, 1 stone here. I know the volumes are the same. So I got P1 minus P2 times V2 is equal to that. If I divide by the volume, I get P1 minus P2 is equal to 1/2 mass over volume, which is density, VF squared, minus 1/2 density, VI squared, plus density, GH final, minus density, GH initial. At this point, we can get everything on, get all the ones on one side. There should be V1s, not VIs. We'll get all the I's on one side, we'll get all the F's on the other side. Because this is love conservation law. I guess technically, yeah, it's just conservation energy. So I got P1 plus 1/2 rho V1 squared plus 1/2, oh, not 1/2 there, plus rho GH1 equals P2 plus 1/2 rho V2 squared plus rho GH2. Yeah, my finals should be 2's. That's a plus. So we have this quantity here, which seems to be the same regardless of where you are. Now there are some assumptions. We are assuming incompressible, and we're also assuming a laminar flow, that the particles are flowing smoothly, there's no turbulence, the particles all move in the same direction. This is claiming that if a faster fluid flows, the lower its pressure is within our incompressible fluids. It holds for compressible fluids also, just the formula is a lot more complex. So if I pull out this and this, part of my inheritance. They held it for a little bit. We have fluid flowing on both sides of the ball. So we have air flowing on both sides of the ball. We have pressure out here where the air is not really flowing. And so these are a higher pressure than this pressure is here. And therefore, the ball, if it tries to fall into the higher pressure, gets pushed back. Now, at some point, obviously, it does fall.